The universe has a heartbeat. It's not the slow, rhythmic pulse of a star or the gravitational hum of a black hole. It is a frantic, impossibly fast tremor, a flicker that occurs 10 million trillion times every single second. This isn't a metaphor. It's a number, 10 to the 44th. That is the frequency of the Planck time, the absolute shortest duration that has any meaning in our current understanding of physics. It's a temporal wall, a boundary. At 10 to the negative 43 seconds, the smooth, continuous river of time we experience shatters into a chaotic, unpredictable cascade. Below this threshold, our two pillars of modern science, general relativity and quantum mechanics, declare war on each other. The very fabric of spacetime, as described by Einstein, is thought to dissolve into a seething, probabilistic chaos, a boiling quantum foam where cause and effect lose their meaning. Our equations, the elegant mathematical symphonies that can predict the orbit of a planet or the behavior of a subatomic particle, simply stop working. They return answers of infinity, which in physics is a polite way of saying we have no idea what's going on here. This isn't just a minor gap in our knowledge, it is the most profound abyss in all of science. It's a fundamental glitch in our description of reality. It forces us to ask a question that sounds like it belongs in philosophy, not physics. Is the universe continuous? Or is it flickering, rebooting its own existence at a rate so fast it creates the illusion of a steady, unbroken reality? What truly happens in that infinitesimal blink? And could it hold the key to a physics beyond our wildest dreams? This boundary wasn't discovered in a particle accelerator or observed through a telescope. It was calculated, derived by the German physicist Max Planck at the turn of the 20th century. Planck was on a quest for something pure, a system of units based not on arbitrary human conventions like the length of a king's foot or the rotation of our planet, but on the fundamental, unchanging constants of the universe itself. He identified three pillars of reality. First, c, the speed of light in a vacuum, the cosmic speed limit established by Einstein's special relativity, linking space and time into a single entity, spacetime. Second, g, Newton's gravitational constant, which dictates the strength of the gravitational force, the very engine that scopes galaxies and bends spacetime around massive objects. And third, h, the reduced Planck constant, the heart of quantum mechanics. It is the fundamental unit of action, of spin, of the inherent discreteness and uncertainty that governs the microscopic world. Planck realized that by combining these three universal constants in a specific way, he could derive a fundamental unit of length, a fundamental unit of mass, and a fundamental unit of time. The Planck length is 1.6 times 10 to the negative 35 meters, a distance so small that if you were to scale an atom up to the size of the known universe, the Planck length would be about the height of a tree. The Planck time is simply the time it takes for light to travel one Planck length. It is the smallest tick of the cosmic clock. But why is this the limit? Why do our theories break down here? The conflict arises from the fundamentally different ways our two best theories describe the universe. General relativity paints a picture of a smooth, deterministic, geometric canvas. Spacetime is a fabric that can be bent and warped by mass and energy, but it is fundamentally continuous. You can, in principle, zoom in forever. Quantum mechanics, however, describes a world that is fundamentally pixelated, probabilistic, and chaotic. Energy comes in discrete packets called quanta. The Heisenberg uncertainty principle states that you cannot simultaneously know a particle's exact position and momentum. This uncertainty isn't due to faulty measuring equipment. It is an intrinsic property of reality. When you try to probe spacetime at the Planck scale, you need an immense amount of energy, concentrated in a tiny volume. According to relativity, this concentration of energy would be so extreme that it would warp space-time and collapse into a microscopic black hole. But according to quantum mechanics, at that scale, the uncertainty principle would cause wild fluctuations in the energy, and therefore in the geometry of space-time itself. Tiny virtual black holes would be constantly popping into and out of existence, tearing the fabric of reality apart. This is the quantum foam. It's the ultimate contradiction, a smooth, predictable sheet versus a chaotic, probabilistic storm. This is the Planck wall. It's where our understanding of a continuous universe ends and the possibility of a discrete, flickering reality begins. From that tantalizing glimpse into time's ultimate frontier, we confront the deepest challenge to our understanding of reality, the nature of quantum gravity itself. The Planck time isn't a measurement we can make with a stopwatch. It's a theoretical construct derived from those three fundamental constants, G, C, and H, that govern the cosmos at its largest and smallest scales. It signals the battlefield where our two greatest theories, general relativity and quantum mechanics, which have been spectacularly successful in their own domains, violently clash. To solve this is the holy grail of modern theoretical physics, to find a unified theory, a theory of quantum gravity. Such a theory would not only explain what happens at the Planck scale, but would also unlock the secrets of the Big Bang's first moments and the true nature of black hole singularities. For decades, the brightest minds in physics have been exploring two main paths into this unknown territory. One path imagines reality is made of unimaginably small vibrating strings. The other path suggests that space-time itself is not a continuous fabric, but is woven from discrete, indivisible threads, creating a granular, pixelated structure. This second idea, known as loop quantum gravity, takes the concept of a flickering universe and turns it into a concrete mathematical framework. Loop quantum gravity, or LQG, proposes a radical solution to the conflict. Instead of trying to quantize gravity on a pre-existing smooth background of spacetime, it quantizes spacetime itself. According to LQG, if you could zoom in on the fabric of reality, you wouldn't find a smooth continuum. You would find a network of interconnected loops, a spin network. These loops are the fundamental atoms of space. They are not space, they space. Each loop has a quantum volume of roughly 1 Planck-length cubes. You cannot have a smaller volume than this. Space itself is granular. From this, it follows that time must also be granular. The evolution of this spin network, the shifting and changing of connections between these loops, happens in discrete steps. Each step takes 1 Planck time. This is the universal reboot. The universe doesn't flow, it clicks forward, frame by frame, 44 times per second. In this model, the smooth, continuous reality we perceive is an emergent property, a macroscopic illusion, born from an underlying discrete quantum process. Much like the smooth image on a television screen is an illusion created by millions of discrete pixels flashing on and off. This has profound consequences for our understanding of the cosmos. Take the Big Bang. In the standard model, the universe begins from a singularity, a point of infinite density and temperature, where the laws of physics break down. But in loop quantum gravity, a singularity is impossible. Because space is made of indivisible Planck-sized chunks, you can never crush matter down to an infinitely small point. There is a maximum possible density. So what happened before the Big Bang? LQG offers a stunning alternative, the Big Bounce. According to this model, our universe emerged from the collapse of a previous universe. As this predecessor universe contracted, its density increased until it hit the maximum limit allowed by quantum gravity. Instead of collapsing into a singularity, it bounced, re-emerging as the rapidly expanding universe we inhabit today. The Big Bang wasn't a beginning from nothing, but a transition, a cosmic rebound. While we currently lack the experimental tools to directly probe the Planck scale and verify these ideas, physicists are actively looking for indirect evidence. They search for subtle signatures of this cosmic bounce in the cosmic microwave background radiation, the afterglow of the Big Bang, or for faint traces of quantum gravitational effects in the light from distant gamma-ray bursts. These theories, from string theory's extra dimensions to LQG's Big Bounce, remain on the frontier of science. They are mathematical poems about the nature of reality. But they all point to the same revolutionary conclusion. The glitch at the Planck time is not a bug in our theories. It's the universe's most fundamental feature, a signal that at its deepest level, reality is not what it seems. Our smooth, predictable world may be nothing but the emergent froth on a deep, flickering quantum ocean.